So guys, welcome back. Today we have the great pleasure to have with us Dr. Skander Hannachi. Skander is a PhD alumni from Tokyo Institute of Technology. He now works with Google at Seattle. He is a machine learning, artificial intelligence, and data science expert. And we have the pleasure to have him right now. Thank you very much, Skander, and let's go.
Yeah, thanks everyone for having me. It's great to be here. It's incredible to work with Dr. Belhaiza again. Me and him go all the way back to middle school, so when we were 12 and 13 years old, and we fought about mathematics then, and we fight about mathematics now. So it's just an incredible privilege for me to be able to work with him and to present to his students. So I'm going to talk about a little bit my path first. So I currently work for Google Cloud. So Google has many divisions, Gmail, YouTube, and Google Cloud is the one which is about providing services to Google's customers. So my day job involves talking to businesses, retailers, banks, insurance companies, airlines that want to build software, and instead of having to hire not hire, but they hire incredible talent, but instead of having to build their own data centers with large servers and those types of things, they want to focus on their own business, and they leave the actual infrastructure, the IT infrastructure, to other companies. So Google is one of many big providers which provides this infrastructure, and that infrastructure is called cloud computing. My role there is more about talking to the customers about their business needs, about what they want to build, helping them design the solutions. I'm not very much a server guy or a hardcore development type person. I'm more focused on the modeling aspects and the business aspects. Before that, I worked for a long time in retail analytics. So doing the same thing that I help Google Cloud's customers do now, but I did it specifically for retailers, and especially the last 5 years before joining Google. So from 2015 to early 2020, I worked for Nordstrom, which is a major fashion retailer in the United States. And before that, I did my PhD and spent long years doing a PhD. And then before that, I was a researcher in Tunisia, my home country, for the National Institute of Marine Science and Technologies. And that was a very interesting role because I was the only modeling and mathematics guy on a team that was otherwise all marine biologists. And there I worked on applying neural networks to sonar images, and I did time series analysis of fish populations. So analyzing like, what will the population of fish look like next year and 2 years from now, and so on. Education-wise, I did a PhD at Tokyo Institute of Technology, as Dr. Belhaiza said. I focused on the intersection of machine learning and quantum computing. My engineer's diploma, which was a 6-year degree. So we have this weird thing in Tunisia where instead of doing 4 years and then an extra 2 years, you do 6 years straight. So I did a 6-year degree in instrumentation engineering. And instrumentation engineering is an unusual degree. I would say that it's about 60% electrical engineering and 40% industrial engineering. And there's a lot of physics involved as well, because you have to learn a lot about sensors, optical sensors, thermodynamic sensors, and so on. So what does a day in my life look like? I spend a lot of time coding. My main programming language is Python, and I use frameworks like NumPy, scikit-learn, TensorFlow. I do some R as well. I do a lot of stuff using Linux commands. I work with database systems. I work with containers, which is a technology that allows people to deploy stuff very easily on cloud environments. And I use a lot of big data platforms. And then I also do a lot of design work. In fact, I'd say that most of my work is spent doing design work, where I put together the architecture of systems, and I talk to business stakeholders, product managers, and to other engineers on what the system should look like and how the different parts of the system should connect to each other. So now a little bit about the whole AI machine learning and what does it mean to be an artificial intelligence and machine learning specialist, it can be kind of confusing because a lot of people use the words AI, machine learning, and deep learning interchangeably. That's not very accurate. AI is a very large and interesting field. And you can break it up roughly into two separate components. One component is symbolic AI. Sometimes it's called GoFi because it's good old-fashioned AI. Symbolic AI is about teaching computers how to reason, how to think about things in terms of their meaning, in terms of their symbols, not in terms of numbers. Because let's go back, take a step back. What does computer mean? Computer is just another way of saying calculator. So calculators just crunch numbers. They don't do anything else besides crunching numbers. Artificial intelligence is about getting computers to think. Now, there are two things that humans do much better than computers. They reason about the meaning and the value of things, not just the numbers, using symbols. And then the second thing that they do, so that's symbolic AI. The second thing computers do better than humans is that they learn by example. So the way, this is the really, really interesting part. Now, consider how a person learns their native language. They don't go study all the rules of grammar for their native language and then start speaking it. They sit there and they listen to their parents, they listen to their older siblings, they listen to their cousins, they listen to the radio, they listen to the TV, and after a few years, they speak their native language properly. So that's what machine learning is trying to duplicate with computers, where they go and they give a large amount of data to a computer, and instead of telling it, oh, here's the rules of how you should treat this data, no, just look at the data, try to learn something from it, and give us a model or a rule after that. So that's machine learning, and that's the part. So within AI, I focus mainly on machine learning. I'm actually trying to get a little bit back into symbolic AI, but that's a very big challenge. It's going to take me some time to get there. Within machine learning, I am specialized especially on something called deep learning and neural networks. And again, a lot of people tend to use the word machine learning and deep learning interchangeably. That's not very accurate. Deep learning is yet a subset of machine learning. And it involves a type of models called neural networks, which, so back to what I said earlier, humans are very good at learning by examples. So one way we try to simulate that on a machine is to actually simulate the neurons of a real human brain. And that simulation is called a neural network. Well, to be precise, it's called an artificial neural network to distinguish it from a natural or true neural network. And a more recent version of neural network is called deep learning. When the number of neurons being simulated gets very large, then we say that the network is deep. So that's deep learning. So that's what I specialize in today, and that's what I work with most of the time. Now, to explain a little bit how a model can learn from data, whether it's a neural network or not, it's usually easy to look at it from a kind of represent it graphically. So you have raw data, you have observations, then you take a human, and that human looks at the data and labels it. So here the labels are like, okay, blue represents one category and red represents the second category. Then the machine learning model, so the human does the labeling. Now there are more recent technologies for doing automatic labeling, but that's a really advanced topic. But at the basic version, what the labeling is done by a human, or it's captured by some sort of instrumentation. And then the machine learning model comes in and tries to find where does the separation happen, or what is the line that mathematically represents the difference between the two categories. Right? And so that's basically almost all machine learning models amount to a algorithm that looks at labeled data or unlabeled data sometimes, and then tries to find where the separation, is there any shape, are there any curves that can describe what the data looks like. So typically machine learning algorithm will take in multiple inputs, and they'll take out one or two, sometimes a little bit more outputs, but definitely multiple inputs. And then the different categories of machine learning algorithms typically differ on the types of curves or shapes that they can figure out. So linear regression, which is typically taught as part of statistics, can actually be considered a machine learning algorithm. And that one does a very simple, like the previous example I just showed you, just a one-line separation. KNN, or K nearest neighbors, but most people refer to it as KNN, is the other way around. It uses almost every data point as an individual representation, and it gives you a very, very complex decision surface or separation surface. And then the more advanced algorithms try to strike a balance between both. So you have support vector machines, tree-based methods, so like random forests and boosted trees. These are very popular as well, not just deep learning. And deep learning models and artificial neural networks are good at finding a balance between the very simple representation that linear regression does and the highly complex representation, too complex. People speak about something called overfitting that a K nearest neighbor algorithm can do. So another way to look at this is in terms of supervised learning. So what is machine learning is often there are different types. There's supervised learning, unsupervised learning, reinforcement learning. Most of the models I worked with have been supervised learning. I worked with a few unsupervised learning models as well. I haven't worked with reinforcement learning, but that's another very interesting topic. Supervised learning, you feed input data and you want to see the output. And the output can be either a continuous value, so it's a regression model. Now, be careful, regression here means regression in general, not just linear regression, any type of regression. Or it's a classification model, so now it's not a continuous output, it's a discrete value. So here's an example of a classification problem that I worked on. This is my very first job back in Tunisia as a data scientist or an analyst working for the marine biology team. We'd go out on a boat and we'd capture sonar images of fish. And this is what the actual image looked like. And then we'd run some processing to obtain things like how long the cluster of fish and how high it was, how far away it was from the bottom of the ocean, how far away it was from the surface of the water, how was it a big cluster of fish, was it a small cluster of fish? We take all of those values, input them to the neural network, and then it would tell us, is this cluster of sardines? Is this anchovies? Is this mackerels? And we weren't doing this just for fun. The reason we were doing this is that when we were surveying the Tunisian coastline to see the different schools of fish, the way they were doing it when we first started was they had to actually do some fishing. So they'd go capture some fish and then use that as in one location and use the sample they captured from that location to make generalizations about the entire region. So they would capture 2 or 3 locations in the southeast coast of Tunisia and then use that, extrapolate that to the whole southern part. Same thing in the Sahel, same thing in the northeast, and so on. So if they had a method of detecting the fish species without having to actually throw a net and catch the fish, then they'd have a much more precise estimation of the fish distributions. That's where this work was going. That was the purpose of this work. So this is an example of classification. Now, you have an example of regression, and in my case, it was a much more specific type of regression, was called forecasting. This is my job when I was working in retail analytics, and when I was working at Nordstrom, was doing this type of model. So in this type of model, the output, like I said, regression, the output is a continuous value. Now, what we would do is we would input historical sales. So we wanted to forecast how much black t-shirts we are going to sell in 3 months. And the reason we want to do that is we want to figure out how much black t-shirts we should order from the suppliers. And we need to do that 3 months in advance because that's how long it takes the supplier to ship the black t-shirts to the store. So what do? We look at, and we want to do this by week, right? So how much should we ship in 3 months and how much should we ship in 3 months and 1 week and so on. So we look at the past 104 weeks, so that's 2 years. So past 104 weeks of sales, we input that into a machine learning model. It would crunch those numbers, and on the other side, it would output what is the most likely value, and then that would be fed into a second optimization system, which would then look at that predicted number, decide whether it wants to go a little bit higher or a little bit lower than the predicted number, and then based on that final decision, it would actually send a file with the desired quantity to the supplier, and then the supplier would ship the shirts back to us. Now, this is demand forecasting, what I was working on in the retail context. There are other types of forecasting. For example, in finance, people do forecast volatility. So volatility is how unstable a stock is. If it's highly unstable, then it's a risky stock to invest in. If it's not so unstable, if it's very stable, then it's a safe stock to invest in, right? And then another application, which a lot of companies, including Google, does, is try to forecast how much usage you're going to require on a data center. So if you are a e-commerce company, so you're a retailer, but now you're working purely in e-commerce. For example, during Ramadan, there's going to be a lot more traffic to your website the 2 weeks before the Eid al-Fitr, because people are going to be shopping. So you're going to need more servers dedicated to your e-com application during that period than you are during the rest of the year. And the more sophisticated companies, what they do is they actually try to forecast the server usage and then allocate numbers of servers accordingly. So that's a really interesting application of time series forecasting as well. Now, this is a really interesting topic. I had pretty much given up on my training in electrical engineering by the time I was done with my PhD, and like now I'm a pure theory and AI person and whatnot. But then when I got into the forecasting space, I realized that a lot of the knowledge that I had from electrical engineering, so Fourier transforms, Laplace transforms, Kalman filters, all of those things came back as very, very useful because they are very applicable to time series forecasting. And the reason why is that time series forecasting can be looked at as a machine learning problem, can also be looked at as a signal processing problem, so filtering. So typically, and if you look at electrical engineering applications, you'll see a signal, a radio signal or a TV signal or something like that, and it will look something like this. This is a very noisy signal, and you want to filter out the noise and keep only the clean signal. And what forecasting really is filter out the noise, keep the clean signal in yellow. Now take that clean signal in yellow and just propagate it forward to see how far, what it's going to look like in the future, right? And so, you know, a lot of people, you know, go into like data science, machine learning. Oh my God, it's scary. AI, it must be really advanced. No, if you have a background in engineering and systems engineering and mechanical engineering, electrical engineering, and computer engineering, and you have a solid background in topics, like I said, Fourier transforms, matrix algebra, Kalman filters, those things, then you are already set. And now you just have to understand what the purpose of the different algorithms are. So the reason why I got into this space into this space in the first place was because signal processing was my favorite thing. But if you asked me when I was a 21 or 22-year-old student in college that what I would be applying these Fourier transforms and Kalman filters to would be shoes and suits and t-shirts, I would have laughed in your face. And yet there I was years later having a ton of fun applying these types of models to predicting fashion items. Now, there's a lot more to this than beautiful models and mathematics. A lot of my work involves architecture. So architecture here doesn't mean traditional architecture, building houses and castles and museums. It means figuring out how the different systems, the different separate IT systems connect together. So how do you connect your database to the server where you're going to run the actual model, to the server where you're going to make the decisions, and so on. So this is an example of architecture which combines multiple things. It combines database tools for storing the data. It combines analytics and machine learning tools for forecasting and running the ML problem. It also combines different separate tools for doing the optimization problem. And by the way, Dr. Belhaiza is a much better expert on the optimization side of things than I am. I focus only on the predictive part. He is a world-renowned expert on this part of optimization. At the bottom here, you see containerized OR solvers. And then how do you consume those and how do you update those? So this is streaming event data coming, updating the data on an hourly basis. And then how do you update and how do you refine your predictions accordingly? So right now, I'd say like my day job pretty much consists of going to business stakeholders, hearing what they need, going to other people who are maybe not AI or ML engineers, but they are more like big data engineers or streaming event engineers or you know, very good at like web traffic type things and so on. And then together we decide like, what should this look like? How do we connect the dots between these different types of systems? And then this is the starting point. And then after that, only after that do we actually start coding these. And most of the time we already have like code that's kind of generic, and it's based on this, we try to refine it. So finally, a topic that I'm starting to get into more and more now is something called ML ops, so machine learning operations. And this is a fascinating topic. So if you look at how data science and machine learning was done initially, you had data, somebody would go in, take a, you know, export a file. It might be an Excel spreadsheet. It might be a CSV file. They'd look at it, then they'd apply some modeling on top of it, and then they just send the decision back. This was a very straightforward and simplistic process. More recent, after the development of machine learning over the last 3 or 4 years, sorry, not last 3 or 4 years, after the last 10 years or so, it's been since 2010 that the word machine learning has kind of like really grown and more organizations are working on it. Typically, instead of having just a simple like extract the data, model it, and then send it back, you would have extract the data, and then you would have a data science platform where the data scientists can go in every day and do the analysis continuously and then send it back. Right? This works for situations where you're doing something pretty basic, like a prediction that has to run every 3 months or something like that. But if you have to do predictions that run every single day or every single hour, for example, predicting what the what people like on YouTube. When you go on YouTube and you search for videos, you as an individual YouTube user, YouTube will actually want to help you find the best type. If you're looking for matrix calculation, then it knows that you're interested in a certain types of topics, and you'll notice that it will actually recommend videos that are similar to the video you just watched on matrix calculation. How is it doing that? It's using machine learning in the back end. In order to do that with a system that's as big as YouTube, or if you have an e-com where it's generating new recommendations for customers, and you have thousands of customers visiting the e-com website every hour, same thing. That's predictions, but those are at such a large scale that you have to retrain the model every day or even every half a day. So for that, you can't simply have a normal data science platform. You have to have full-on machine learning operations. So you have to have a system where you're managing multiple models, making sure that the data is consistent, making sure that it's being refreshed frequently, making sure that once a model is trained and we're happy with the training, it can get pushed back to the system without any problems, and making sure that you're monitoring so that if the model starts giving bad predictions, you capture it immediately. You don't have to wait several days until the business comes back and says, hey, our sales have gone down because your model is bad. No, you detect it immediately. So this field is machine learning ops. This is what I'm trying to learn right now. I've just started my journey on it, but it is an absolutely fascinating journey for those who are interested. So with that, I look forward to your questions, and I'll hand the mic back to Dr. Belhaiza.
Okay, thank you very much, Dr. Skander. Thank you very much. Guys, if you have any question, please raise your hand and unmute yourself. Any question, Abdulaziz?
لا دكتور
we can't hear you well.
I couldn't hear you.
Okay. Okay, I'll go with the first question myself. Maybe the guys will are a little bit shy, I understand it. So what is exactly, I mean, now you're doing right now? I mean, you're dealing with businesses trying to implement the Google Cloud services, and how does this relate exactly to exactly your main field of expertise?
Well, I speak to Google Cloud's customers specifically in the cases where they want to do a machine learning application. Mm-hmm. They want to build a security application, or they want to do some sort of digital transformation. They want to build an e-com website, something like that. I don't. That's not my specialty. I only talk to those when the requirement involves some sort of machine learning model or some sort of data science aspect.
Okay, so is it basically trying to transfer, I mean, sell your expertise in machine learning to other businesses instead of having them build their own teams and stuff like this?
It's not so much the expertise per se, it's more helping them design the solution. So they will have an idea on what machine learning they want to do already. They might consult with us and with myself as like, can you help us on the decision of the model? And so there's a little bit of that part where like I'm giving the expertise of the modeling itself. There's also a second component where I'm giving not so much the expertise of the model, because a lot of companies have very sharp data scientists on staff, but on here's how you're going to build that model if you want to use Google Cloud.
Okay, another point I wanted to ask you about, Skander, is how just, I mean, to put us in context, because we'll be starting the topic about discrete Fourier transforms this week with our students. And how does this prepare us to neural networks, in fact?
So for neural networks specifically, it does so in many ways. The first way it does it is that you learn discrete Fourier transforms. You get used to how signals are represented. And so okay, let me take a step back. So first, like this, just the overall mathematical framework gets you ready for dealing with something like neural networks. But more importantly, if you look at a Fourier transform, theoretically speaking, it's essentially a representation of a function, of an arbitrary function. So you have a function with any shape you want it. You want to represent that as a combination of different sine function or cosine functions. And a neural network is really doing the same thing. It takes an arbitrary function, which is the function that we want to learn from our data, and it represents it, but now instead of representing it as a series of cosines, it represents it as a series of kernels, if it's a kernel-based neural network, or it represents it as a combination of sigmoid functions, if it's an old school perceptron neural network, or modern day deep learning models typically will use what's called a rectified linear function. So the philosophy of taking a bunch of small functions and using them to a combination of them to come up to represent a complex function is, you already understood that when you understand something like the Fourier transform and the Fourier series. And then once somebody explains to you how a neural network does it, it becomes a lot easier to understand. So that's one way it helps. A second way it helps is that for a lot of types of problems, you can actually do the Fourier representation of a signal first as a pre-processing step and then feed it into the neural network, and you can get better prediction results if you do that instead of just representing the raw data itself.
So can I say just, I mean, roughly that, in fact, the Fourier transform helps figuring out the kind of learning function we can get at the end, right?
Yes.
Exactly. Last thing I want, maybe I'll pass the hand to one of our colleagues too, Ali, Dr. Ali, who's with us too. And I want to ask you about how important is it, how matrix completion, and if you remember last week, I told you that we just finished the topic about compressed sensing and matrix completion. How important is it? I mean, how accurate is the forecasting or the prediction if, in fact, we had incomplete data at the beginning and we try to run some algorithm to fill in the gaps? And how important is it?
Matrix calculations is not just important, it's critical. If you don't know matrix calculations, you can't do machine learning. Now, when you first start your machine learning journey, there are tools like NumPy and like TensorFlow will handle a lot of the matrix calculations for you. But as you move and you get more advanced in your machine learning journey, you will have to understand what the matrix calculations are happening in order to frame what your problem is. And it happens with neural networks. It happens with linear programming models. It happens with estimating the accuracy of a model. If you apply machine learning to image and video problems, then that's end-to-end matrix calculations. If you're doing like a operations research problem like quadratic programming or linear programming, you have to understand how to represent a business problem as a matrix first before you feed it into the, typically like there's a discipline actually called problem framing, where given a business problem, a business person will come, he'll describe the problem, but they're not a mathematician. It's up to you to understand what the shape of that problem looks like mathematically before deciding which machine learning model to use, or whether it's even a machine learning model or an operations research model or another type of statistical model. And in order to do that, you're going to have to leverage your understanding of matrix algebra from beginning to end.
Okay, thank you, Skander. Maybe one of the guys have a question. Okay, I think they are. Abdurrahman, you have a question?
I think I saw it in text.
Okay, Abdurrahman is asking a question. He has a problem with his mic. Maybe he's asking if there is any AI that formulate the problem for me. Any?
No, we don't have an AI that can formulate the problem for you. There are AIs that can help you figure out which one of the, if you saw like the screen I presented earlier where there's different types of models, so if you go here, like you have different types of neural networks, you have decision trees, support vector machines, and so on. There are AIs which will tell you which one of those to choose. So an AI is looking at the problem, and then from it looking at the problem will tell you which. So an AI is choosing AIs. And that field is called AutoML, for automated machine learning. At Google, we have something called neural architecture search, which is one type of AutoML. We also have another service called Wazir in Arabic, which does Bayesian optimization, which is also another way of doing AutoML. There are other tools, for example, AutoSKLearn and AutoKeras are open source tools which do AutoML. Now, all of these, you give them the problem, instead of having to figure out which algorithm to use yourself, AutoML will tell you which algorithm to use. But framing going from business problem to the mathematical formulation, not yet. Hopefully, we might be there sometime in the future, but now, no, not yet.
Okay, Firas, you have a question? Go ahead.
Yes. First of all, thank you for this great talk. You have mentioned earlier that part of what you do is working with customers. So yeah. I know that the coding part is fairly easy, but how do you translate the customer needs and problems to a full machine learning project?
So that is, in part, it's going to require a lot of experience. In part, there is more and more material available on the web on the topic of problem framing. So problem framing is when you are trying to, you talk to a customer and you figure out like, okay, I need to understand what type of problem they're trying to solve first. And questions you'll ask is are you trying to figure out a decision, or are you trying to make a prediction? I'm giving you a simple example of problem framing here, right? So if you're trying to make a decision, is this something you want to decide? Okay, great. Then you probably need an optimization algorithm. If you're trying to make a prediction, then you probably need a supervised learning algorithm. If you're just trying to understand the structure of your data or the structure of your consumers, the structure of your market, then that might be an unsupervised learning problem, so a clustering algorithm. So I can't really give you a straight up like here's a basic method. I just can tell you it requires a lot of experience. It requires talking to business people. Business people typically don't know that much math, but they do know a lot about their domain, and they can help you and guide you a long way with their domain expertise. And then there is an increasing amount of literature on problem framing. So it's always useful to read up on that. And I can send you a link on that later if you're, I'll send it to Dr. Bahaiza and you can look it up.
Okay, thank you, Skander. Question from one of our industrial engineering students. He's asking, as an industrial engineering student concentrating on data analysis, what advice would you give us? And what skills should we learn, and what areas should we refine ourselves at?
Industrial engineering students are very, very well positioned to just go into data science directly. Their training typically is perfect for the field. They know a lot about optimization. They know about, they understand like, kind of sort of the connection between the math and the business. That's what, in fact, I'd say that is what industrial engineering is. It's like looking at business from a mathematical point of view. They understand like project plans, critical paths. I would say an industrial engineering student might want to focus a little bit more on their programming skills if they do want to go into data science and AI, because once you get into that field, you'll find yourself working with computer science students who can typically, like, they get an idea and it takes them only one afternoon to code it. And myself, that was something I struggled with when I first started my PhD. I'm an electrical engineering person. I was much more used to circuits and to hands-on experiments. And so going from the math to the code took me several days, whereas computer scientists, once they get the math, it takes them like 2 hours to go to the code. So the only thing I'd say to an industrial engineering student is just try to practice your coding. Coding is not a theoretical skill. It's very much like a sport, like going to the gym or jogging or playing basketball. You have to just code and code and code and code and code. Put 2-3 hours. If you're a student, you don't have kids, you don't have time, you still have some time on your hands. So just put several hours a day into coding for a year or two and you're good, you're golden.
Okay. Well, let me see if there is any other question we can take, or so thank you very much, Skander. It's been a long time I didn't see you, and I can't thank you enough, honestly. It's very late at Seattle right now. Thank you for all this preparation and all the things you presented. Thank you all guys for presenting, and hope to see you next, guys, with another seminar. Thank you very much again, Skander, and talk to each other soon.
Yeah, inshallah. Take care, guys.